Hello everyone, welcome back to Bites of CSC. So in this lecture, we'll be talking about the backpropagation of error. So till now, we have done the gradient descents and different types of gradient descents, but I have not really explained that how the error is propagated in a deep learning network. Now, I'm afraid that this is a little bit math heavy part, but I'll be trying to explain that using a story so that you can understand or memorize the concept better. So this is your neural network, and let's start with the story. Say there are three friends, and let's name them as like A, B, and C. So they have gone to a foreign land, and only A knows the local language, whereas B and C, they don't know the local language. Now, for some reason, there has been a fight between A and C, and now they are not talking to each other. And whenever they need to communicate, they have to communicate via B. So now C goes out, and since he doesn't know the local language, there was some problem, and he apparently had flouted some traffic rules, and he was given a ticket. Now when he comes back, he's very afraid that what does this mean, like he's not sure what to do. There's just a date and time given. He has to meet the officials, but he doesn't know. He needs to know some information about what might be the consequence of this ticket. Now they have three neighbors, and now A goes to each of the neighbors and tries to find out that what could be the meaning of this ticket. So the first one says that he is going to be fined around 200 bucks, I think. The second one, who looks a little nervous, he in fact got nervous, and he said that, oh, he has got a ticket, they will harass him, fine him a lot, even put him behind the bars if the officer has a racial bias. The third person seems to be a cool man, and he says that, oh no, the officers are just going to interrogate and warn him, and that's it. Now, see, whenever we meet a person, even we don't know for sure that if that person is reliable or not, but looking at the person, how he talks, what he wears, we kind of, make a preconceived notion or about the person, like how reliable the person can be. So, similarly, A also has some preconceived notions about his neighbors. He thinks that he's a very wise man. This person seems like a little bit who panics a lot, and this person seems too casual. So, taking all the information, uh, keeping that in mind, that how reliable each person is, he forms an opinion like he will surely be interrogated. He can be fined a lot, and I'm not sure if they will lock him up. Since we are foreigners, rules aren't very transparent here. Now, this line is not spoken by any three of them, but this is he infers because he sees that there is like three people has reacted in three ways. So he actually takes all the common points together, and then he makes up his mind that probably the rules aren't very clear or aren't very transparent. Now let's get back to this neural network and try to find out that what is happening over here. So say this is your A, and now he is getting some information from these three neurons. And since, as I said, that A will attach, he has some preconceived notion about his neighbors. He has attached some weight to all whatever has been said to him by his neighbors. So let that be W1, W2, and W3. And actually, W1, W2, and W3, they do not have to be same. They can be different, and they can also be same. There is no hard and fast rule regarding this. And now, when we come to this part, rules aren't very transparent here. What is actually happening in neural network concept? This is actually where A is adding some activation function to whatever has been said. So there is a little bit of distortion of information according to his understanding. So here also in a neural network. So first they weigh the whatever the information a neuron obtains, and then the neuron adds an activation function, like it passes on this information through an activation function, which in human context I'm drawing an analogy with his own understanding, and he makes up some output, and now this output he will convey to B. Now B will also take the information, and now B thinks that A is not liking C these days, and he has many factors to weigh in. Like A looks a little bit grumpy. I don't know if A has interrogated or has really done a good research on this topic. So there are many things going on in B's mind. So B will also add some weight to whatever A has said and an activation function, and B will say that, well, I think they will warn you. Like he's now trying to make up his mind that what he will convey to C, and he also needs to make sure that C isn't very he already is nervous. He doesn't want to make him more nervous regarding the matter. So he says, just keep some 4 to 5 thousand bucks with you. They might find you and highlight that you're new here and you do not know the local language. Anyways, keep the number to our embassy and call me if they do not listen to your explanation. So whatever A has said to him, he has actually added some activation function, and he has just change the information just to make it appear less gross to C. So now C takes in the information, and C already knows that B loves him, and B is trying to cheer him up and make him feel that okay, it's all right, it doesn't matter. But getting from whatever B has said, he applies. Now he adds that weight and he adds the activation function, and he says that, oh, I have landed in a big problem. Now let's stop over here. So this is the output we actually hear. So now this is known as the forward pass, when an information is transferred from this neuron to the output neurons. So what is happening here is, now we move on to the mathematic part of it. So we are actually finding the weighted sum at neuron J in layer L. So we are taking any neuron J which is in layer L. So this is the activation function. This is the so what we are actually, a neuron is transferring to another neuron is the output of this activation function. So this is the activation function of neuron J in layer L, and this is what will be transferred to the next neuron. And now Z is calculated as K equals to 1 to N, which denotes that how many neurons are connected to this particular neuron. For example, if you consider this neuron, 3 neurons are added. So K will be equals to 1 to 3. So for each neuron, it will multiply the connection weight and whatever has been passed. So what has been passed? This is basically the output of the activation function, which is coming from this layer. So when this neuron is passing on information to this neuron, what it is passing on is the output of the activation function, not the Z. It is actually passing this information. So that is actually multiplied with the weight. Like for example, in this case, what we saw was whatever A said was the whatever information he collected, he added the activation function, and that was actually conveyed to B, and B added his activation function on this part and added weight to this part. So here also we are multiplying that with the weight with the activation function, the output of the activation function of the previous layer, and with that we will be adding a bias factor. Now this has been discussed in detail in my MLP lecture. I would request you to go through that to understand this better. So now let's move on to the story. So now when he goes to the office, he finds that the rules are very transparent and this is same for all. It is not that the foreigners will have a different rule. The officers were very nice to him and he just had to pay $100 as a fine. So there was no problem. So what is happening here is this is the output and this is your target. What is the reality? Now, here we need to adjust whatever information he got versus whatever information he like whatever activation he used, and he needs to find. So next time when some information, like when conveys some information to him, so that he doesn't make the mistake or he doesn't get too much worried or anything. So what happens here is, first we will compute the error in the output layer. So C here is the cost. Cost means whatever has been predicted minus whatever was the reality. So this is the target and this was the prediction of the neural network. So the difference between the prediction and the target is the cost. The error which I had been talking about in the gradient descent lecture, this is same as that error, which I'm calling it as cost as per the convention. So this is the output neuron, say J. Now what happens here is, there are two things. Number one, he attached some weight factor to whatever B had said to him. And number two, he used an activation function. Like he made it his own. He had to understand, whatever was said to him, he used his own understanding. So here we have to weigh in two things. First of all, he need to adjust the weightage he had put whatever has been said to him, and number two, he needs to also adjust the whatever, like if he has understood that completely, if there was some problem with his understanding. So that is depicted by this. So we are actually finding the partial derivative of the cost with respect to the weighted sum. So this is whatever B has conveyed into W, which gave him this. And that is to be multiplied by whatever the mistake in the understanding was, which is, in neural network context, is the partial derivative of that weighted sum with respect to the activation. This is how the output layer error is computed, which is depicted by this. That is error at neuron J in the output layer. So for each neuron, you need to calculate this. Now just not the output neuron, that is C in the diagram, but B and A, which is the hidden layer neurons, they too also have to rectify their mistakes. Now the thing is that whatever assumption is made, the final assumption will always be made by C. That is, in neural network context, it is always the output neuron which will make the prediction. So basically, the hidden neurons do not have any direct relationship with that cost factor, but they do owe something, like because it was their information, it is based on their information that the output neuron will be making its assumption or will be giving its prediction. So what happens here in this case is, C will come back and C will say that this is what I expected and this is what happened, and based on that, B will need to weigh in, or we will need to consider that what is the information, what information it should have passed. Like it will find out its mistake based on whatever assumption C made and how it went with respect to the final target or the reality. So now we are to find out that how a hidden layer neuron computes its cost. So now, since they do not have any direct relationship, so in this case, what happens is, this is what, say this is this like layer L plus 1, say this will be the output layer neuron. So the output layer neuron here computes the uh, mistake regarding the cost, that is, it calculates the partial derivative of cost with respect to its weighted sum, and that information is passed to this neuron. Say this is the B as in this diagram, and now B tries to rectify its mistake based on that information to whatever the information it passed. So that is computed, that is, this is multiplied by the partial differentiation of the weighted sum of the next layer to with respect to the weighted sum of its own. So in this way, actually recursively, so similarly B will now pass on the information to A. Now A will try to find out, gauge its mistake, and so that the next time it informs B, or it passes an information to B in a manner that that will be more or less tweaked in a way so that ultimately C gets a more authentic information based on which it can make more realistic assumption about the situation. So here the summation sign is because see, in this case there were just single neurons, but in this case if you consider this diagram, so this particular neuron is sending information to both the output neurons here. So there are two neurons, and in this case both the neurons in reality will be sending the information, the error information, back to this neuron. So therefore it finds out the mistake it made in this case, and it also finds out the mistake which it made while passing the information to this neuron, and based on that it will just add up both the mistakes, and it will find out whatever the error it had incurred in its own assumption. And similarly for this layer 2. So this is given by this formula, and this is the error of neuron J at some hidden layer L, whatever layer L. So chain differentiation has been used in this case. So partial differentiation of cost with respect to the weighted sum of that particular layer for that neuron is going to be the summation, where uh, the partial differentiation of the cost with respect to the weighted sum of the previous layer of the, like, not the previous layer, sorry, of the next layer, that is multiplied by the, because this is the direct relationship is between this neuron and this neuron and not this cost. So therefore it will need to use the chain differentiation in order to find out this particular case. So here del zk of L plus 1 divided by del zj of the layer L. Now based on this, finally the weight updation will be made. So we all know in the previous gradient descent algorithms that ultimately the weights and the biases, these are the parameters which needs to be changed or adjusted accordingly with the, so that the error is minimized. So this is the error which has been incurred, and now what happens here is we need to update the weight, and that is given by, so this is the gradient of the cost with respect to the weight, which is given by the, this is the output of the activation layer of the previous output of the activation neuron of the previous layer, and that is multiplied with the error incurred in that particular neuron J. And in case of bias, it is just the gradient will be equivalent to the error that has been inculcated. So why do we actually multiply this? Because actually we had, when we were trying to find out the zj, we actually multiplied this activation with the weight, the activation that was received from the previous layer with the weight. So in this case we will need to consider this activation function, the output of the activation from the previous layer. Whereas in case of bias was just added to activation into weight. So therefore bias has no relation with this particular activation. So therefore the gradient of the bias will be just the error of the current neuron, which is J. So this is how the errors are actually back propagated. So in forward propagation, the predictions are made, and in back propagation, so neuron by neuron, the error calculation is done and the weights are updated for each neuron. And this is how the uh, backpropagation algorithm works. So that's all for today, and thank you for watching.